Hi, it's Nelly. In our last lesson, we explored the hydrosphere to find out where we would find water on our planet. We found water in several places, but realized how little fresh water there is for us to use. We were actually exploring one of the many cyclic global systems that take place on Earth, the water cycle. This cycle helps us to explain how it is possible to maintain life on Earth with such a small percentage of fresh water. Just think, the water we are drinking would probably have been drunk by dinosaurs millions of years ago. In fact, there's a rumor that within our lifetime, the water we get from our taps has been through about 7 other people before us. This is all because of the way water is cycled on our planet. It is cycled, not destroyed. This is really important because if we had no water, there would be no life on Earth. As simple as that. Now, water, like all substances, has certain properties. Properties are characteristics that explain a substance's behavior. Water would not be able to cycle as it does on our planet if it was not for its special properties. But what are these special properties of water? Well, that's exactly what we're going to explore in this lesson in order for us to better understand why water is so important for life here on Earth. I think you may be surprised to see how many of these properties you already know of. By the end of this lesson, you will be able to describe the microscopic model of water, use this model to explain the properties of water, and investigate the properties that make it possible for water to cycle and to support life on Earth. Firstly, we need to investigate some chemistry and learn about the microscopic structure of water. Without understanding the small stuff, we cannot explain the big stuff. If you look into this beaker of pond water that I've collected, what can you see? Nothing really. But what would we see if we look at a sample of this water using a light microscope? These organisms are called protists that live in the water, and they are about 1/10 of a millimeter in size. But we still cannot see the molecules that make up the water itself. Do you think we would be able to see the water molecules if we magnified the sample even more with an electron microscope? These instruments can magnify things by up to 1,000,000 times. Well, actually, no. We couldn't. So, how can we see what water molecules look like? The truth is that we can't. Scientists have done many experiments and investigations into molecules and the atoms that form them. And it is from these experiments that they now know that the water is made up of covalently bonded oxygen and hydrogen atoms. This model is about 160 million times larger than a real water molecule. This oxygen atom shares a pair of electrons with each of these hydrogen atoms. So, the formula of water is H2O. Let's have a look at an animation to see how these water molecules form. Diatomic oxygen and hydrogen atoms react and bond to form water molecules. Do you see how the oxygen and hydrogen pair shares electrons to bond covalently? This creates an angular molecule. The oxygen atom has a stronger attraction to these shared electrons because it has more positively charged protons in its nucleus than hydrogen. The negatively charged electrons are more attracted to the oxygen protons. This causes the oxygen end to be more negatively charged and the hydrogen side to be more positively charged. Because of this, we call the water molecule a polar molecule. So, back to the water in our glass. There are millions of these water molecules in this glass. How are they arranged? Well, the negative oxygen of this polar molecule is very attracted to the positive hydrogens of other water molecules. This attraction is very strong because of intermolecular forces between water molecules called hydrogen bonding. Scientists called it hydrogen bonding because the forces of attraction are so strong that it was as if the molecules had actually bonded together. In actual fact, it is not bonding at all. No sharing or donating of electrons, just very strong intermolecular forces. These three diagrams show the arrangement of water molecules in three phases: gas, liquid, and solid. I would like us to now discuss each one of these phases in more detail. We will start by looking at water molecules in the liquid phase. In a liquid, the water molecules roll over each other, keeping an attraction between one another. These forces of attraction are what make water so important. Without these forces, water would be a gas at room temperature and there would be no life on Earth. When water is heated, the molecules are energized and move faster and faster. When particles are moving, they have kinetic energy. When they have enough kinetic energy to overcome the strong intermolecular forces of attraction, they fly away from each other and form water vapor. Now that we have seen the microscopic model, let's investigate the phase changes of water by melting some ice in the sun and taking some temperature readings. Water is a solid, or ice, at temperatures below 0 degrees Celsius. It starts changing phase and reaches its melting point at 0 degrees Celsius. The interesting thing to notice is that as long as the ice is melting naturally, the temperature remains at 0 degrees until all the ice is gone. Only after the phase change is complete does the temperature slowly increase to room temperature. When heat is added to the liquid water, the temperature rises steadily. But watch what happens as the water starts to boil. As the liquid water changes phase to become a gas, you should notice lots of bubbles form in the liquid and rise to the surface. These bubbles contain water vapor. Obviously, all of the water does not become vapor all at once. Now notice that even though it is continually being heated, the water remains at a constant temperature of about 100 degrees, depending at which altitude you are doing the boiling. We can summarize what we have just observed in a temperature versus time graph. This graph is called the heating curve for water. Let's analyze this graph more closely. Notice that there is a large difference in temperature between the melting point, 0 degrees, and the boiling point of water, about 100 degrees Celsius. This large difference in temperature is because of the strength of the intermolecular forces, hydrogen bonds, found in water. Remember, there are a huge number of hydrogen bonds in a single glass of water, and they require lots of energy to break. So, water can absorb a lot of heat before changing phase from a solid to a liquid or from a liquid to a gas. Water can also lose a lot of heat energy before it freezes. Now, at the average temperature on Earth, water is found in its liquid form. Large changes in temperature from this average are needed to cause water to freeze or boil. This is also important in lakes and oceans because they can store, transport, and release heat during changes in weather without the temperature changing very much within the water. The temperature of the oceans is very important as it powerfully affects Earth's weather and climates. When water cools, the water molecules have less kinetic energy and the temperature of the water decreases steadily. But close to 0 degrees, the molecules begin to rearrange themselves and form lots of hydrogen bonds. In a solid, the water molecules are arranged in a regular pattern called a lattice. This regularity causes the molecules to be further apart than when they roll over each other in liquid form. This means that ice takes up more space than water. Try this as an experiment. Fill 2 plastic bottles with water. Next, place one in a freezer. What predictions can you make? Have a look. The frozen water now has a greater volume. The mass of the water did not change, so this means that ice is less dense than liquid water. Because ice is less dense than water, it can float on top of liquid water. In colder regions where the temperature drops below 0 degrees Celsius, rivers and lakes freeze over, but plants and animals can still survive in the water below the surface ice. So far, we have shown that the special intermolecular forces between water molecules are called hydrogen bonds. Hydrogen bonding gives water all its special properties. Let's look at some more of these. Hydrogen bonding creates a phenomenon called surface tension, where the molecules at the surface of the liquid are attracted to each other sideways and downwards, causing them to stick together. So, the surface of water behaves like an elastic skin that can support a downward force. This surface tension allows insects to walk on water or mosquito larvae to live in still water and breathe through the surface. Please remember this fact if you have still water in a lake, pond or reservoir near where you live. Still water should always be boiled before drinking to make sure it's safe. You can also experience the strength of water tension if you jump off a diving board into water. It sometimes stings you, isn't that right? Another property that hydrogen bonding creates is cohesion. The word cohesion means to stick together. Let me demonstrate. This is a very simple experiment that you can also try for yourself. Take a coin and simply drop some water onto it. What happens to the water? The water groups together in the middle of the coin. The water molecules form droplets because they are attracted to each other more than they are attracted to the surface they are on. This property of water molecules is called cohesion. In this glass, however, the water molecules are more attracted to the glass than they are to each other, so they spread out and fill the glass. If we pour out the water, the glass is still wet inside. This phenomenon is called adhesion. The word adhesion means to stick to something else. The molecules now have a stronger attraction to the glass's surface than to each other. Due to cohesion and adhesion, water is also able to move up tubes against gravity. The thinner the tube, the higher it can move up. This very special property of water is called capillarity. This animation shows how cohesion and adhesion assist in capillarity. Do you see that because water adheres to the side of the tube, it moves up? But because the molecules also stick to each other, the molecules in the middle are pulled up as well. Capillarity is very important for plants because it enables water to move up the stem into the higher parts of the plant. The final property we will investigate is the dissolving power of water. We know that water is a very good solvent because many substances can easily dissolve in water. But did you know that 50% of our blood is made up of water, while the other 50% is made up of cells and proteins and dissolved ions? These dissolved ions and floating substances can be transported around the body and used where they are needed because of water's good dissolving abilities. I am sure that you'll agree that water is an incredibly amazing substance. Without it, there would be no life. On that note, here's your task for today. Investigate which substances dissolve in water and which substances do not. You need to test substances from your kitchen or environment. Try to categorize what kinds of things dissolve in water and what things do not. Once you have conducted your investigation, remember to write a report in which you discuss your method and results. See if you can explain why water is able to dissolve substances like table salt, but not chalk, by referring to the microscopic model of matter. Do join me for the next lesson when we will look at chemical changes taking place as part of the water cycle. Goodbye. You will be able to describe the microscopic model of water, use this model to explain the properties of water, and investigate the properties that make it possible for water to cycle and to support life on Earth. Firstly, we need to investigate some chemistry and learn about the microscopic structure of water. Without understanding the small stuff, we cannot explain the big stuff. If you look into this beaker of pond water that I've collected, what can you see? Nothing really. On Earth, the water cycle. This cycle helps us to explain how it is possible to maintain life on Earth with such a small percentage of fresh water. Just think, the water we are drinking would probably have been drunk by dinosaurs millions of years ago. In fact, there's a rumor that within our lifetime, the water we get from our taps has been through about 7 other people before us. This is all because of the way water is cycled on our planet. It is cycled, not destroyed. This is really important because if we had no water, there would be no life on Earth. Hi, it's Nelly. In our last lesson, we explored the hydrosphere to find out where we would find water on our planet. We found water in several places, but realized how little fresh water there is for us to use. We were actually exploring one of the many cyclic global systems that take place on as simple as that. Now water, like all substances, has certain properties. Properties are characteristics that explain a substance's behavior. Water would not be able to cycle as it does on our planet if it was not for its special properties. But what are these special properties of water? Well, that's exactly what we're going to explore in this lesson in order for us to better understand why water is so important for life here on Earth. I think you may be surprised to see how many of these properties you already know of. By the end of this lesson,